Hello, my name is Axel Armando,
My name is Ivan Minauro.
and we're going to present our autonomous navigation model with extended common filter.
First of all, what's the extended common feature? Well, it integrates odometry, estimations, and Aruco code detection to ensure a better estimation of the robot's position, and it's divided into two phases. First of all, the prediction. It relies solely on the odometry and your data collected from the wheels, so that and also the uncertainty grows a lot over time, so that you know a rough estimate where the robot is actually positioned, and the correction. It extracts established position of the Rucos and other metrics to minimize the error between the real robot and the estimated robot. The odometry node that we're utilizing, first of all, it takes information from the encoders. It takes the position of the Rucos using the camera simulated in the environment, and M matrix that it's it contains all the information from the Ruco positions and the covariance. This to go on with the corrections that will get us a better estimate of our position compared to the real robot.
As a main navigation algorithm, we decided to go for bug 2. It has a superior robustness compared to bug 1 or other types of bugs due to it containing a progress line marked from the starting point into the target point. This is enhanced by using the odometry, of course, and the LiDAR data to fully identify obstacles such as walls and other geometries. The behavior of this autonomous system goes into a change between going to the angle or the point where the target is located, the avoidance of walls and adhering to these walls for it not to go off into a different direction, and it reassesses back the trajectory it has to go to after successfully avoiding a wall.
Next, the results after testing our model, we estimated, and the estimated robot by the odometry with the common filter, we got our biggest errors were that it distanced itself by around 0.2 meters in the x-axis, and in the y-axis it distanced itself like around the 30 centimeters, giving us a max position error of 0.36 meters and an angle of 13 degrees. However, our average was much less. In average, we had a rough estimate difference of around 5 centimeters in the x-axis, 7 centimeters in the y-axis, and an angle of less than a degree of separation.
Through the areas of opportunity, we could have improved in the ways we could have improved this project much more. We could have improved the observation model, in which we could have added the Aruco's orientation to improve the angular estimation. We could have used the covariance inside the simulation in a way that we could simulate the noise particular to the environment to enhance the extended Hammond filter. And in the bug 2 algorithm, we could have included more protocols and more actions to avoid dynamic obstacles or greater emergency situations. And in conclusion, we can say that the extended common filter improves radically the odometry and the positioning estimate of the robot, both reducing errors in our simulated environment and in the real robot. This complexity of the filter, although hard to implement in a code or in an integrated environment, it improves localization and accuracy much more than only using odometry or other non-calculated options.
Thanks for your attention.
Thank you.